Discuss at the end. Okay, let's begin. So we have been looking at techniques to digitize our signal, and if you basically think about it, till now we have come up with two different algorithms for digitizing. What are they? What are the two ways in which we digitized? One was flash, where you basically took the input and compared with all reference voltages in one shot. And what was the second one? SAR ADC, which was essentially a binary search, where instead of comparing with all reference voltages, you compare only with relevant references. And it turns out in practice, these are the only two techniques or algorithms based on which we digitize the signal actually. Okay. On top of it, we have a bunch of techniques which can be used to improve the resolution of the ADC, and that is what is done to increase the speed or improve the resolution. And that's what we look at in the rest of the lectures. So whatever techniques we'll discuss now, they can be applicable to either a flash or a SAR, right? So throughout this lecture and in the few classes, whenever I draw an ADC like this, basically it's a quantizer. It can be quantized either using flash or using SAR. Either of them will work. So let's start looking at one such technique to increase the resolution. So let us say I consider an ADC. Again, this could be flash or a SAR. So let me try to model the ADC mathematically. So how will I model the ADC? How can I mathematically model the ADC? Simplest model for the ADC we have seen, right? Mathematically, if I have to represent the operation of any ADC in general, right? That is for sampling. After sampling, basically first I sample it, that is done. Let's assume that's done. So let's say this is some sampled y of n. Then I want to get the quantized output. How did we model this? This is the input, this is the output. How did we model the quantization operation? Assume that we had a quantization noise added. Right? So let's say this is Q1 of it. This is how we model, right? Now let us say I want to increase the resolution of the ADC. In that case, what can I say about Q1? If I increase the resolution of the ADC, what can you comment on Q1? It should become smaller and smaller. And let us say I make an ADC with infinite precision. So at the output, what can you say about Q1? 0. It will tend to 0. So in that case, if I look at the output, what will it be equal to? Y of n. It will simply be equal to y of n. Right? So now forget that this is an ADC, right? This is some system that you have, discrete time system that is given to you. Here output is y plus q1. I want the output to be y. What is the simplest thing I can do here? Remove minus q1. Yeah, I have to remove q. So what is the operation I have to do here? I have to subtract what? Q1, right? So basically, that's basically adding minus q1. Now you remember that this is now an ADC. So this is basically this. So which means you cannot access Q1, right? It's not an independent signal. So how can I get Q1? I have only access to the input of the ADC and output of the ADC. So how can I get Q1? If I take the difference between the output and the input, I'll get it. So let's say I do this. If I do this, what will be the signal I get? Minus Q1. I see I need minus Q1 here. So I'll just go and correct it. So this seems like it's a great idea. So why don't we do this in practice? I mean, I'm sure you are convinced that there is some catch in this. That is why in practice we don't have an infinite ADC, right? Infinite resolution ADC. So what is the catch here?
Why this addition of second addition is
This is why this is a digital data. I'm subtracting the digital output. I mean, addition subtraction. Assume that there is no issue as such. Sorry. P of n is no. For any it doesn't matter, right? I mean, I can always represent the quantized output as input plus some error. It all depends on what is that error. I don't know that error, but I can always say that my output is input plus some error. That error is no, right? I mean, basically, I don't know this error. I'm estimating this error and subtracting it.
One question before this. If we wanted V of n, right? Why we wanted again Y of n again? What is the meaning? Then what is
this is the digital output, right? You want an ADC, which means you have to take the analog signal, digitize it, and make sure the output is as close to the input as possible. So here the idea is we wanted to reduce the quantization noise.
And this subtraction, the second, then V of n will be a digital output.
Exactly, right?
That will be an analog output.
So that's the problem.
That was addition is not.
Okay. I mean, I thought you were talking about this. So this one, you see, I mean, as he pointed out, this is an analog signal. This is a digital signal, right? So you can't subtract an analog and a digital signal, right? So this could either be subtracting two analog signals or two digital signals. So let me just copy this ones. So let me actually do some color coding. Let us say things in green are all digital, things in pink are all analog. So let us say, I mean, now there are two possibilities, right? I can implement this guy so that we subtract two analog quantities or two digital quantities. So let us say first try to make it full digital. So let us say this is digital. I want to implement the subtractor in a pure digital domain. So this is done. This is all digital. So here this is an analog signal. I want to convert it to digital signal. What do I need? We need one more ADC. Right? So let's see. If I do that, then this will be done. So let's say this is ADC2. Let's see. This is going to add its own quantization noise. So what will be the signal here? Yeah, I mean, in terms of the inputs, y plus q2. So this is what? So what is the signal you get here? So what will be the output if I add it? So it looks like this is not helping. So let's try the other way. That is, we'll try to see if we can implement the subtractor in analog domain. So here I have it. So I already have this guy in the analog. This is digital. So let me write it. This is as of now digital. So what do I need? I need to put a DAC. So then it will become an analog signal. So one thing to note is this DAC here is taking the digital data and converting it to a signal, and that signal is still a discrete time signal. Yeah, I mean, it is not a continuous time signal, right? This entire model is operating on discrete time signals. So the DAC is simply going to do the following. It is going to take the digital data, say it looks like this, 1, 2, 3, 1. It is going to take this digital data, convert it to some voltages, say V0, 2 V0. It is not converting it to a continuous time signal, right? And this can be done without any issues. And we even saw how we can do it in a SAR. In a SAR also we had that capacitive DAC. So conversion from digital to discrete time samples is straightforward. We can do it, and we can do it without any error. So the crucial difference is when we had an ADC here, even without going into circuit level non-idealities, the act of adding an error introduces quantization noise, right? But when you are having this guy, when you are having a DAC here, by default the DAC is not going to add any extra noise. Okay, so let me erase this. So now, which means this is now an analog signal. So what will I get here? What will be the signal I get? Yeah, I mean, what is the signal? Analog signal, but what? Yeah, which is look carefully and tell me, what is the signal you get here? Minus Q1. Okay. So now I have the analog signal. Finally, I want everything digitally. So what should I do? I mean, this is an analog signal. Finally, I have to do the operation digitally, right? I want a digital data. You should put another ADC. So actually, let me erase this. Hold on. Make some space. So looks like I have to go and put another ADC here. That will add its own quantization noise Q2. But one thing to notice, this ADC or the input here is minus Q1, right? That is the quantization noise coming from the first ADC. So let us say the first ADC was a 3-bit ADC. So it is having a range minus Vref to plus Vref as usual. So what will be its step size, delta or delta 1? 2 Vref by 8, right? That's 2 Vref by 2 power 3. If that is the case, what can you say about the range of values that Q1 can take? It will span minus delta by 2 to plus delta by 2. So which means Q1 will take minus Vref by 2 power 3 to plus Vref by 2 power 3. So now if I go and directly feed this guy to the second ADC, now remember second ADC is also operating in the same range, right? Now remember, if you want to get the maximum resolution from an ADC, you should get the maximum signal to noise ratio, which means the signal power must be maximum, right? Which means the signal should span the entire range of minus Vref to plus Vref, right? If you give a signal with a smaller range, the signal to noise ratio we get from the ADC will be smaller. So here the signal is minus Q1, which spans this range. So to squeeze out the maximum signal to noise ratio from this ADC, what should I do? I should amplify it so that it spans the entire range of minus Vref to plus Vref. The signal to the ADC must span the full scale range of minus Vref to plus Vref to get the maximum signal to noise ratio or the maximum resolution from the ADC, right? So here it spans only 1/8 of that range. So to get the maximum out of this ADC, what should I do? I should amplify it. And what is the value of this gain? 2 power 3. I'll write it like this. Huh? Fine, no? Let's put it in silent mode. Yeah. So let's do that. So now let's look at what signals we have. This is the output of the first ADC V1. Let us say this is the output of the second ADC V2. What is V1? Y plus Q1. What is V2? What is the signal? Minus G times Q1. So V2 is minus G Q1 plus Q2. So now you look at these two signals. Remember, the whole goal was to go and cancel the quantization noise of the first ADC. That is the thought process with which we started this entire journey. So look at these two guys and tell me how should I process the two digital data V1 and V2 so that Q1 is completely cancelled. Yeah. So our other way to do is, right? Both are similar, right? So if I do it, then you see what will the output be here. Here it's Y plus Q1. Here it will be minus Q1 plus Q2 by G. So basically these guys cancel. You only have this. And in this case, we have chosen the gain to be 2 power 3. So this is 2 power 3, 2 power 3. Right? So now you see that at the output we have quantization noise of the second ADC, but it's getting scaled by a gain. So there is definitely some improvement. So let us see how much improvement we get. So again, for example, let us say the second ADC is a 4-bit ADC. So the quantization noise Q2 corresponds to an ADC with the 4 bits of resolution. If that is the case, what can you say about Q2 by 2 power 3? How many bits of resolution do you think it will cover? 7? Everyone able to get it?
Yes.
Okay, so see, let's start this, right? If it's Q2 by 2, right? Okay, how did you say it was 7? What told you?
Just applying the range of the cube.
That is simplest thing, right? So if you already saw, if it's a 3-bit ADC, the range is this, right? Now for a 4-bit ADC, the range of Q2 will be 2 power 4. So if I divide it by 2 power 3, right? So this is going to correspond to 7 bits. So what we have done essentially, we have taken a 3-bit ADC, a 4-bit ADC. We have done some arrangements here, so that overall we get an ADC with an effective resolution of 7 bits. Okay. So now let me redraw this guy in a more formal way. So this is the input Y. I give it to the first ADC. This is the output here. So what do I do next? What should I do? First ADC is there. What am I doing? No, that's what. What did we do now? First ADC was there. We basically have to convert this to an analog signal using a DAC and subtract this. That gives the quantization noise. And remember, the direction for DAC is this. And this is amplified, and in this case, if this is a 3-bit ADC, this was 2 power 3, and then given to the second ADC. And the way we process the data is V1 plus V2 by the gain. And when we do that, we saw the output was the input plus the quantization noise of the second ADC divided by the gain. Right? So that should make you ask this question. Looks like at the output, the improvement I get depends on this gain G. So why don't I keep increasing this gain?
Because the gain should be minus 50.
Right? That's clear? So the reason we chose was to keep this input range to be within minus Vref to plus Vref. That is why we took this guy multiplied by 2 power 3. If you scale beyond that, it will exceed. So what will happen? Yeah. That's what, if I let's say the gain is greater than 2 power 3 here, what will happen?
Saturate.
It will go beyond, so what? So saturate, so what happens?
It won't be doing this, it will not be following Q1 affair.
Yeah, see, remember this whole affair was to cancel Q1, right? So we are getting an estimate of Q1, digitizing Q1 and then subtracting it. If the input to the second ADC exceeds its range, the ADC is not functioning properly, it's going to get saturated. You will not be able to get an estimate of Q1, so this cancellation will not happen properly. So it is really crucial to keep the signal here within the range. So which means the maximum gain I can set is determined by the ADC you have here, right? And this G max. So now let's quickly generalize it. So let us say this is a B1 bit ADC. So what should be the gain here? 2 power B1. So the gain max is 2 power B1. And let us say this is B2 bits. What will be the overall resolution I get from this? B1 plus B2. Great. So now let us say I don't choose this gain to be the maximum gain. And remember that we are choosing this gain to be this maximum value so that we can squeeze out the maximum performance out of the second ADC, right? I can even use a smaller value of gain. In that case, I can't get the full resolution from the second ADC. So there will be some drop in the overall performance.
How do you do this by G?
It's all digital, right? So as I was saying, let us say this gain here you are using less than the maximum value. So which means you will not be getting the maximum performance from the second ADC, but still you will get some improvement. It will not be as much as using the maximum gain, but you will still get some improvement. Let us see how much will be that. So that means, again the output is this, right? Y plus Q2 by G. So let us say Q2 corresponds to B2 bits of resolution. I have a effective quantization noise which is Q2 by G. Now G is some general number. So how many bits do you think this will correspond to? Huh? Sorry? It's not, yeah, it's not any number, right? Any number. I mean, we are generalizing it now. If let us say Q was 2 power B1, what would you say? B2 plus B1. So now it is some number G. What will happen? Log to the base 2 of G. Fine? That's all. So this is the general improvement you get, and the maximum value of G is this 2 power B1. So the maximum you can get out of this is B1 plus B2. That should also make logical sense. You have a B1 bit ADC, B2 bit ADC. So at the max probably I can get only B1 plus B2. Okay. Cool. So okay, now let's answer his question. How are we going to do this operation of this B1 plus B2 by G? So let's take this example. Say first stage is 3 bit, second stage is 4 bits. So which means I will be combining the output as V1 plus V2 by 2 power 3. So V1 is a 3 bit data. So let us say it is something like this: x1, x2, x3. These are all ones and zeros, right? Similarly, V2 is 4 bits. So let us say it is y1, y2. All xk's and yk's are all either ones or zeros, digital data. Okay. So now let's see how we can do this. Or before that, let us see how we can even do V1 plus V2. The reason I am asking is I can do this in two ways, right? Basically, I can write V1 like this and V2 like this, or I can write V1 like this and V2 like this, right? So in the first case, I have aligned the MSBs. This is Y1. It's not. In the second case, I have aligned the LSBs. I can add, if you want to add these two, I can add it in two ways, looks like, but what is the right way to do? First one, Y. Second one, Y. Okay. Okay, let's look at, right? So
X1 and Y1 are the MSBs.
X1 and Y1 are the MSBs. Okay, let's see, right? So let's take example again. So V1 is 3 bit, right? So it's a 3 bit ADC. Let us say the range of the ADC is 0 to Vref, single ended for simplicity. What will be the step size delta 1? Vref by 8. So let us say my output V1 is 3 bit, right? So let's say it's 110. It is 6. So if the digital data is 6, what will be, how will I say the equivalent analog voltages now? I have input which I have quantized to a digital data of 6. So if I had to say approximately this is this much voltage, this is digital data. I am asking if I had to convert it to an equivalent analog voltage.
Okay. 6 into 1
6 delta 1, right? So which means this will be 6 Vref by 8. Similarly, second ADC is 4 bits. What is its delta? Delta 2? Vref by 16. So let us say V2 is, let's say 1001. This is what? 1001 is 9. So if I were to convert this guy, what will this be? Now if I were to add this, what happens? And basically you multiply this by 2, multiply this by 2. So it's 12 plus 9, 21, right? So if you think about it, what we are doing, I had 9 and I am adding what to it? 2 times 6. It is not just 6. So 12 is 1100, right? So we are not basically doing this. We are not taking this guy and then adding it like this. Okay. Right? Simply because the first bit is the MSB bit. You can think of it like this, right? Let us say we are doing a fully differential one. The thing is spanning from minus Vref to plus Vref. The MSB bit what does it tell you? If the MSB bit is 1, what can you comment about the input?
Greater than Vref by 2.
No, the range is minus Vref to plus Vref.
Acha, greater than 0.
The MSB bit simply says if the input is positive or negative, right? So I mean, so it's basically saying like, you know, have plus some number, plus some let's say decimal, I mean integer point and fractional point. This is sign, so let us say plus this, and the other case it will have something and then plus. So you will be trying to aligning these guys when you are adding, right? You will not be aligning the opposite way, isn't it? So you keep the MSBs aligned. Is that okay? So the correct way to add is this guy. So in our case, what we are doing, this is x1, x2, x3. v2 is y1, y2. But we are not adding the 2, we are dividing v2 by 2 power 3. So if I divide a number by 2, what happens? A digital data, you divide, it gets right shifted. So it gets right shifted how many times?
3 times.
So 1, 2, 3. So rest are all zeros, right? These are all assumed to be zeros. So I add it, what do I get? That's all. So this simply boils down to taking the two data v1, v2 and simply concatenating them. Right? This addition operation, although it looks like we have to do addition, if we choose the gain to be this maximum gain of 2 power 3, this simply boils down to taking the two data, stitching them together and sending it out. And note that this will work only if the gain is chosen as this maximum value of 2 power 3. If it is chosen anything other than 2 power 3, it will not come like this. Okay, cool. So let me do this. So it's time to learn some jargons for you to remember. So this technique is called a two-step ADC or two-step conversion for obvious reasons. So the first ADC here is called the coarse ADC. Makes sense because we saw that the output is stitched like this. The first ADC gives the MSB bits. As you know, MSB gives the coarse information about the input. So if this guy is called coarse ADC, what do you think this is called? Okay, terminology is fine. It's fine ADC. So here, what is the signal I get actually? Yeah. I mean, let's say this quantization noise is Q1 and Q2. What will I get here? Minus Q1. So this guy is often called the residue signal. So if this is called residue, the amplifier that amplifies a residue, what do you think we'll call that as? It's amplifying the residue. What will I call it? Yeah, it's residue amplifier, that's all. Sometimes also abbreviated as R. And just to summarize, the output is reconstructed as V1 plus V2 by the gain. And if you do that, we get the thing as the input. So you take the second stage output divided by the gain it sees before and add it with the first stage output. And when you do that, you see that the quantization noise from the first stage completely gets cancelled, and that from the second stage is again divided by the gain you have before. And the maximum value for this gain is 2 power B1. If you do that, the effective resolution you can achieve is B1 plus B2. And even the reconstruction is simple. You just take V1, V2, just concatenate the two and send it out. Okay. So if the gain is not equal to this 2 power B1, it is some number G. What is the effective resolution I can get? It's not B2. I mean, look carefully. It's Q2 by G. So what is the resolution? B2 plus log to the base 2 of G. So note that the effective resolution it only depends on this backend ADC and the gain you have. This guy, the first ADC, it is not affecting the resolution directly.
B1, right?
It is not B1. Which one?
B1 plus log.
No. That's what, right? It's Q2 by G, isn't it? Q2 corresponds to an ADC with B2 bits of resolution. Okay. Plus you have this improvement due to G. Okay. So the point is, the effective resolution you get will only depend on the backend ADC and the gain you have before it. So the previous stage ADC doesn't directly affect the resolution. How it is affecting the resolution indirectly? Yeah, it just sets the maximum value of the G, right? But final resolution you get only depends on the gain you use here. Okay? That is something to always remember. So now we have a two-step ADC. What is the next thing to do? Huh? 3 steps. How do you get a 3-step ADC? Just write this here. Yeah, I mean, simplest way is to assume that you are making a 2-step ADC once again, but the second ADC is another 2-step ADC. Right? That's how we do it recursively. So let's quickly do that and then generalize it quickly. So let us say this is my second ADC in a 2-step ADC. Okay. So the second ADC itself is a 2-step ADC. So let me rename these guys. So let us say these are all V2, V3. So this is ADC2 giving quantization noise Q2, ADC3 with quantization noise Q3. This has B2 bits, this has B3 bits, this gain is G2. That 2. So what will be the maximum value for G2? 2 per? 2 per what? B2. So now if I were to treat this as an ADC, how will I reconstruct the data V2 hat? I mean, assume that this is now an ADC, right? How will I get the data once? I want one single data out. I have two V2, V3. How will I reconstruct?
V2 plus V3
by G2. And if I do this, I will get, let's say the input here is some V in, or let's say Y hat. This will be Y hat plus Q3 by G2. So now this is the second ADC. I'll go and put the first ADC before this. So I'll have the first ADC here. This is ADC1. So this is, let us say, B1 bits. Quantization noise is Q1. This is the actual input. I'll go and compute the residue. I'll put a DAC1. This. So here I'll use again G1. So G1 must be, what is the maximum value for G1? 1. So what will be the signal I get here? Minus G1 times Q1. Fine. So I'll replace this. So Y hat is. So now we can treat this entire thing as some ADC whose output is V2 hat, right? So I have, although I have 3 stages, now I can think of it as though this is my first ADC, this is my second stage. So how will I get the final output V? I have 2 ADCs, V1, V2 hat. What should I do? G1. And I know what is V2 hat. V2 hat is this guy. I go and plug this in. What do I get? This is getting divided by G1. So what do I get? V2 by G1. And remember that this is also equal to, I know the value of V2 hat, right? So remember, I'll also, we were doing this. So this is what gave rise to this. I also know the value of V2 hat here. If I plug that here, what do I get? Yeah, first let's write V1 is what? It's y plus q1 plus, it's y plus q1 plus, I know V2 hat is this guy. So this is getting divided by G1 and added here. What will I get? Minus q1 plus q3 by, so obviously q1 cancels. So once again I end up with, so the logic is this, right? So if I have 3 stages, the output of the third stage is divided by the gain it sees before, which is G1 times G2. You get this? The output of the second stage is getting divided by the gain it sees before, which is only G1, and the first stage comes directly. And if you do the reconstruction this way, the quantization noise from the first and second stages, they completely get cancelled. The only thing that remains is the noise from the third stage, and that is suppressed by the overall gain you have before. So once again, if I keep the, if I choose G1 to be the maximum value and G2 to be the maximum value, what is the effective resolution I will get? B1 plus B2 plus B3. Okay. And once again, if I choose this maximum value, if I have the 3 data V1, V2, V3, how will I get the final digital data? I'll simply concatenate like this. That's all. So this is a 3-step converter or a 3-step ADC. Now of course you can make it an n-step ADC. So I'll just write the final stuff, I'll not draw it fully. If you have an n-step ADC and say in the kth stage, the ADC has a resolution of bk bits, quantization noise is qk, and I use a gain of gk. How will I get the final data? I have V1, V2, V3 till Vn. How will I reconstruct?
V1 plus.
Just to note that when I had a 3 stage, it was V1 plus V2 by G1, V3 by G1, G2. So now that will just keep extended. So this is V2 by V3 by G1, G2 plus it will continue till Vn by G2 till Gn minus 1. And if I do that, at the output I'll have the input plus what will be the quantization noise that remains? The last stage quantization noise divided by this guy. And if I choose my all gk to be the maximum value of 2 power bk, the effective resolution I get is summation bk of, and again the output, even this operation of summation is straightforward in this case. I just have to concatenate all the data like this. Okay. But now let us say here I don't use this maximum value for the gain. I use some random gains G1, G2, G3 and all. What will be the effective resolution I get? I get at the output the quantization noise is Q1 by this guy. So what will be the overall resolution I have? Bn plus log to the base 2 of this entire gain. Okay. Cool. So now we have it. Let's look at how this will be operating in different time instance. For that I'll take a 3-step ADC as an example. I have basically 3 ADCs now, ADC1, ADC2, ADC3. So okay, let me not write here. So let us say in the first clock cycle, the first ADC process samples the input. It makes decision in the first clock cycle TS. Then this guy goes to the second ADC, right? So it will finish its job in the next clock cycle 2 TS. Then it will reach the third stage, and the third stage will finish its job in 3ts. Now then, one thing you can do is you can make sure the second input is sampled after this. So 4, 5ts and 6ts. So my IN2 comes here. So which means the first data is available at 3ts, second is coming at 6ts. So this is one way in which you can do. And here you see what is the effective sampling rate I have gotten. Fs by 3, right? So is there something better you can do?
You can increase the throughput, right?
Yeah.
You can give it that depth. Right?
So basically, when the second ADC is processing the first input, ADC 1 is sort of free. You can make the ADC 1 start processing the second data now. I'm sure you have seen this thing, right? So what is this called? Pipelining, right? So this is called pipelining. I mean, and it's actually not quite new, right? Who do you think this overall principle of this general principle of pipelining? Who do you think started this? It's a general principle, right? It is not in circuits.
It's very ancient. Like
Yeah.
very old thing.
Turns out Henry Ford started this to optimize assembly line, right? When they're making cars, you don't wait one guy to make one thing, give it to the next guy and do it.
Yeah.
And that's how he optimized the assembly line, and that started kind of the manufacturing thing, right? So if you do this, this will be called pipelining, and obviously now it will be called the pipeline ADC. So now what we are doing, when the first ADC is finished its job, you don't keep it idle in the second clock cycle, you make it process the second input. So which means the second input is now fed to the second ADC here. Now what can I do to the first ADC? I can ask it to process the third input. So which means IN2 comes here. So when can I get the second output now? At 4ts I can get the second output, right? This output 2, this output 1. So this way you see that at each clock cycle I get the output. So the overall sampling rate is still Fs. I have not compromised on the speed. But notice that there is a delay, right? Because if I just had one ADC, after one clock cycle I will get the output. But now after how many clock cycles I get the output? After 3 clock cycles is when I get the first output, right? So there is a additional latency of how many cycles? No, 3, but 2. Additional is 2. So in general you have additional latency of n-1 clock cycles. That is something you can't remember. So one minor thing here. So if you do this pipelining, remember in a 3 stage we were combining the outputs as V1 plus V2 by G1 plus V3 by G1 G2.
You need to be careful. The take n-1.
Yeah. So here you see at, let's say at this time instant, the first, third ADC is giving the result corresponding to the first input, whereas the second ADC is giving result corresponding to second, and the first is processing third input. So I can't take this guys directly and add it. What should I do? I have to delay, right? So the first ADC output I have to delay. How do I delay digital data? No, digital data, exact delay I want, right? I want it by, let us say, exactly 2 clock cycles. I didn't expect so much of a pause. Okay. I mean, you understand, right? What I have to do is, I should not be processing the first ADC output at this instant. I should be processing the data 2 clock cycles before, isn't it? So I should be taking the output here, delay it by 2 clock cycles, and then feeding it. Okay, I'll just tell, right? I mean, you have to use a D flip-flop. You just put a D flip-flop, so you put 2 of them with appropriate clocks. Yeah, you think about it. For the second, it's 1. Okay. So this is how you'll have to recombine. So cool. So now you see pipeline ADC is a nice technique through which you can take multiple ADCs. Let us say you have two ADCs of B1 and B2 bits of resolution. By wiring them up in an appropriate manner, we can increase the overall resolution, but without compromising on the speed. Okay. So in practice, if you want to increase the resolution without compromising the speed, pipelining is the way to go, and that's what is done in practice. Cool. So now that we have come up with something, we'll do the following, the same things that we have been doing. We look at what are the things that can go wrong here, try to come up with solutions for it, and then look at the full circuit implementation. Now, of course, you guys know how to implement each of these blocks here, but we'll still put everything together and see how it turns out. Okay. And for understanding what can go wrong, let me consider a simple two-step ADC. So I've already drawn. Wait. So I'll take a simplistic case where this is a 2-bit ADC. 3-bit ADC. So the gain here should be maximum of 2 power 2. So here if you notice, I just have an ADC, a DAC, and an amplifier. So only these three guys can have any non-idealities. So let's look at issues with each of them. So let's start with the ADC. What are the things that can go wrong in an ADC? If you have a general ADC, what are the non-idealities that you can expect?
It's not linear.
Huh?
It's not linear.
Okay, non-linear. What else?
That ideal
INL, DNL, right? I mean, but finally, at the end of it, you can think of it like this, right? Any non-ideality in this can be thought of as having shifted characteristics like this, right? Can be gain error, offset, INL, DNL, anything. At the end of the day, it all maps down to the fact that the switching thresholds of the ADC, they are incorrect. So let's first look at this ADC non-ideality. So for that, again, let's take this example. So first I'll consider a case where the ADC is ideal, and let's see what happens, and then we'll see what happens if we have an error. So I've assumed a 2-bit ADC. So ranges from minus VREF to plus VREF. Let me sketch the characteristics of this. This is the input Y, output V1. So let us say this is minus VREF and plus VREF. I'll normalize it to VREF. Okay. So it's a 2-bit ADC. What are the voltages with which I'll compare the input?
0.
2-bit, right? So first is 0 and then half and minus half, right? So this is, let us say, plus half. So let's draw the characteristics. So if it is between 0 and half, what is the value to which I'll quantize the output to? No, 0 and half makes sense to quantize to somewhere in between, right? So we'll do it 1/4. So let's say this is 1/4. Similarly, okay, let me write this is 1/4. Similarly, this will be this 1/4, and here what will be the value I'll quantize it to? This is between half and 1. I'll quantize to 3/4. Similarly, I'll have this. Again, everything is normalized with respect to 0. Okay. So let us say this is my straight line that just. Now let me also sketch the quantization noise on the same axis. I mean the same thing, Q1, that is also normalized to VREF. So how will it look like? How will I get the quantization noise? I have to subtract the input from the output, right? So I have to subtract the straight line from this step characteristics. So at this point, you'll have a jump, right? And what will the jump be? It will go from 1/4 minus 1/4, right? And remember that when the input is increasing, the quantization noise will decrease, right? And at this point, it will be 0. So this is that point where it is 0. And then it will go down, and again at half, it will do another jump. So here also similarly. Right? And as you see, the quantization noise is basically bounded derive by 4. So which means in this case, if I remember this is my Q1 or minus Q1, if I use a gain of 2 power 2 which is 4, the output here will span the range minus Vref to plus Vref. That's what we saw, it's all fine. So now let me do this. Now let us say there is an error. Let us say this switching threshold of this ADC is slightly shifted to the left by a small amount like this. The rest is all fine, only that level is, let us say, messed up. So what will happen to the quantization noise? Now the jump here, where will it happen? It will shift to the left, and you see that at this point the quantized output is 1/4, but the input is some negative value. So 1/4 minus a negative value, it will be greater than 1/4. So the quantization noise will grow beyond 1/4, and at this point, so what is the observation? If we have any error in the switching thresholds of any of the comparators, what can you say about the bounds of the quantization noise? It can go beyond. So if this goes beyond Vref by 4, when I scale it by a factor of 4, it will overload the second ADC. It's a huge problem, right? So what is the solution, do you think? See, you can say that I will go and design this guy properly, but remember, however hard you try, there is always going to be some error. So finally you will end up exceeding the range. So what is the solution? Decrease the gain, that's the only thing, right? So solution for this is to reduce gain. So right now, I'll say that I choose my gain to be less than the maximum gain, which is 2 power 2. So what do you think I can choose my gain to be? Maximum gain is 4. What do you think I can choose? Let's say I choose 3. So if I choose the gain to be 3, I'll reconstruct the final output as V1 plus E2 by 3. So which means now you see that I have to divide this guy by 3, or alternative thing is to say I'll do 3 V1 plus V2. That is also fine. So which means I have to multiply this by 3. And remember, multiplication is a non-trivial operation. You'll have to spend more effort in doing it. But in general, multiplication with what kind of numbers is easy? No, everything is a binary number, right? Powers of 2 is easy because it's simple left shift, right? So which means usually instead of choosing any arbitrary value for gain, we choose the gains to be powers of 2. So our maximum gain was 2 power 2. So what do you think I can choose my gain to be? 2 power 1, which is 2. So if I do that, I will reconstruct as V1 plus V2 by 2, and this is how I will get. And let us say Q2 is a 3-bit ADC. What will be the overall resolution I have? 4 bits. Okay. So now let's look at what will happen to the addition process. So V1 is a 2-bit, it's like this. V2 is a 3-bit output, it's like this. So earlier, if I were using this maximum gain of 2 power 2, I'll be dividing this by 4. So V2 will be right shifted twice. Yeah, now it will get shifted only once, like this. So rest is all zeros. So now when you add it, you see that now this addition is something that you have to do. Okay. Earlier you could just concatenate. Now that's something you cannot do. And if you add these two guys, the result will have how many bits? How many bits will the final result have after addition? Huh? Depends on, but
What is the worst?
it can have 5 bits, right? So you see that at the output I can essentially have a 5-bit data, but the overall resolution I get only corresponding to 4 bits. This is very similar to the redundancy we saw in a SAR ADC, right? In a SAR ADC also, to account for errors, we added more comparisons. So at the output we have more than n bits, but the effective resolution corresponded only to n bits. This is very similar to that. So this is also redundancy. So this redundancy is there to make sure that even if you make an error, or if you don't, it's not like you make an error, even if there is an error in the comparator switching threshold, the second input for the second ADC doesn't grow beyond this range, and the pipelining operation still works. And that is why you have this extra 1 bit of redundancy. Okay, so now let's quickly generalize. So let's say I have first stage having a resolution of d1 bits. So what will be the gain I choose here? What should be the gain I should choose? 2 power b1 minus 1. So which means I will say that the first stage here has 1 bit of redundancy. I mean, I can also choose my gain to be smaller than that, right? I can even say it's b1 minus 2. In that case, it has 2 bits of redundancy. That is, this stage itself has this much redundancy. So then let's play this game. So let us say now I have a case where this is say 4 bits. I choose a gain of 2 power 3. This is, let us say, 3 bits. So I choose a gain of 2 power 2 and 3 bits here. What will be the effective resolution I get from this pipeline? No, please check carefully. Yeah, okay, yeah. It is 3 plus 2 plus 3, 8 bits. So here, if we just count the total, it's 10 bits, but the effective resolution I get is only 2 bits, right? That is because we have 2 stages here. Each stage, 3 stages here, and here the first and second stages have 1 bit redundancy each. So there is 1 bit of redundancy because you have chosen the gain to be 1 power lower. Here also I have 1 bit redundancy. So overall I have 2 bits of redundancy. Again, the point to remember is the effective resolution is only dependent on the gains you have here and the last stage ADC. Okay. Cool. So now we know that if you make any error, we are still okay. That is because of redundancy. Even if there is an error in the comparator switching threshold, we are still okay. So what is the next question to ask? I know that if I make an error, I can correct for it. What might be the natural question to ponder next? We saw it in a SAR, right? I mean, how much is the error we can make, right? So that we can make, make calculated errors we can do. And for that, let me actually take this characteristics, the 2-bit thing, because this will give interesting result. So the question I'm interested now is this, right? I know I'm going to use a gain of, for a 2-bit ADC, what will be the gain I use? What will be the gain I use for a 2-bit ADC? 2, right? I'm going to use a gain of 2. And so which means at the output I have this. I want to make sure this is less than Vref. I'm interested to see how much is the error I can make in the switching threshold, that even if when I use a gain of 2, the output is within the limit. That's the question I'm asking. So let us say I'm looking at this guy. Okay. So remember, this is 1/4, right? So if 2 times Q1 should be within Vref, what should be quantization noise? It's 1/2, right? Basically Q1 is Vref by 2. So this is 1/4. I want the difference between 1/4 and the input to be this to be half. So what should this be? This is 1/4. I want the difference to be half. So what should this value be? Minus 1/4, and that is here, right? So which means I can make an error till this much. So if you do that, the quantization noise, what will happen to it is this. So it will keep growing and reach 1/2, and then it will go down and start like this. Now similarly it works in the other side also. This level can go to the right side by how much? I mean, here we are shifted left by how much? What is this point? Yeah, it's, I mean, in terms of this, it's this. What is this point? From 0 we have come to minus 1/4. We are still okay. Similarly on the right, how much I can go? 1/4. So the tolerable error in the comparator offset is plus or minus Vref by 4. So actually one more thing. So right now we considered an error in this guy. Similarly, if we were to make an error here, how much is the error do you think we can make here? Same. Okay, let's quickly verify that, right? So again, the question is, this error, this switching threshold, which was ideally at 1/2, I'm interested to see how much it can move to the right, right? And remember, this value is minus 3/4. I want the difference here to be half. So this has to be 1/4 again. Okay. So again, this can come till this much. And in this case, if you sketch the quantization error, I'll let you work out. You can work out the quantization error. It will again be within Vref by 2. The same will happen for this guy also. Even this guy can come to the left by 1/4 and will still be okay, right? So let me summarize the observation so that we can make some conclusion. So what we have seen is this switching threshold, which should have been at 0, even it comes to the left and reaches this point of minus 1/4, it is okay. Similarly, this switching threshold, which should ideally have been at minus 1/2, if it comes to the right to minus 1/4, it is okay. Same is for this. So this can come to the left to 1/4, this can come to the right to 1/4, will be fine. So this made someone think, and
in that case, you will miss one of the bits, right?
no, right? What will we miss?
If both of one comes here and this comes here, the one
That's exactly now I'm getting it, right? So you got the thing, but I know you have reservations about it. Let's come to that. So the deal is this, right? I know that if this comes here to 1/4, it is okay. This comes here to 1/4, it is okay. So why don't, instead of having 2 levels, why don't I merge the 2 and have 1 level here? Earlier, I mean, right now I'm having 2 levels, I mean 2 voltages to compare, one at minus half, one at 0. We just saw that if this comes to minus 1/4, and similarly if this comes to minus 1/4, we are okay. So which means I can simply go and make that as my new reference. Similarly, this guy, we saw if it moves to the right to 1/4, it is okay. And by extension, this voltage 1/2, if it moves to the left and reaches 1/4, it is okay. So instead of having 2 different levels, I'll just simply merge them. I'll quickly explain the motivation for that. So this is now, sorry. So this is now minus 1/4 plus 1/4. So the quantizer characteristics will now look like this. In this range, you quantize it to 0.
It is mid-range.
Half. Huh?
It is mid-range, right?
Mid-rate, yeah, exactly. And the motivation to do is the following, right? See, here I have only 2 voltages to compare. So how many comparators I'll need here? Here how many I needed? 3. I have reduced the comparators by 1, right? And this is good because in the pipeline, as we saw, the overall resolution only depends on the last stage and the gains we have. I don't care how many bits I have here. Remember that this resolution of this guy just sets the maximum value for this gain. And we obviously are not going to use a maximum gain. So this does not play a role. So which means that, let us say I choose a particular value for this gain. So for that gain, I'll use the minimum number of comparators in the ADC, so that even if I make an error in the comparator threshold, the gain times the quantization noise is within the limit. That is the thought process, right? You don't need to go and have so many comparators in the ADC because that is not dictating my overall resolution. I am only interested to have some gain here. And we have to make sure that even if I make an error in the comparator threshold, the gain times the error here should be within the limit. So I'll try to figure out what is the minimum number of comparators I need to have in each ADC so that this condition is satisfied. And as we'll see now, for this 2-bit case, or for a gain of 2, you don't need to have 3 comparators, we can have only 2 comparators. So let me copy paste this. So here I'll draw the input output line. So we'll have something like this. So here if I plot the quantization noise, this is, sorry, it's not Q, this is Y. If I plot the quantization noise here, this is the axis. I'll have the jumps around these points, right? And the jump will be, what will be the height of the jump? What will be the height of the jump? Oops, sorry. Okay, something is wrong. Just 1 minute. Yeah, so here if you plot the quantization noise, we'll have jumps around here, right? So it basically will jump to something like this, and then it will do this. And here you can see, right? So even if this guy moves to the left, I'll use different color. If this guy moves to the left from minus 1/4, it can, even if it comes to minus 1/2, that is same as what we had for a normal 2-bit. So the quantization noise will be fine. Similarly, this guy, even if it moves to the right, it can reach till 1/2, and we'll still be fine because that's what we saw last. Okay. So even in this case, if we make an error of plus or minus Vref by 4, 2 times quantization noise will be within the limit. Okay. So for a gain of 2, you don't need to have 3 comparators, you can as well do with 2 comparators. So now we have total of 3 levels, right? So if you have 3 levels, how many bits is it quantizing into? I mean, if I have 4 levels, I say it's 2 bits. 8 levels, I say it's 3 bits. So 3 levels, what is the?
But we require 2
Huh?
log
to the base 2 of 3, right? And log to the base 2 of 3 is around 1.5. So it's usually referred to as 1.5 bit stage. Now similarly, you can also come up with 2.5 bit, 3.5 bit states, where the logic is this, right? You let us say for a 3 bit, normally with 1 bit of redundancy, what will be the gain you use? For a 3 bit maximum, sorry, 2 per 2, right? This will be the gain you use, right? You'll use 2 per 2. So what you do is this, right? Okay, so here for a 2 bit case, the tolerable error is plus or minus Vref by 4. Similarly, you can work out what would be the tolerable error here. For a
plus minus delta by 2.
Yeah, you can work out, right? I'm not giving the number, you can work out. So let us say if you use a 3 bit quantizer with 7 comparators, you work out what is the tolerable error. Now you figure out what is the minimum number of comparators I can have here, so that even with the tolerable error, for a gain of this, the gain times quantization noise is within the limit. That will give you the 2.5 bit stage. Similarly, you can generalize. And this was popular in the olden times, simply because, see, now let us say I have this 3-level comparator. I can use a gain of 2. Or I'll just say it's 1.5 bit stage. So I can have, let us say, multiple copies of this guy. So let's say at the end I put a 2 bit. What will be the overall resolution I get? It will be 2 plus 1, 3, 4, 5, 6. Can have 4 more and get a 10 bit ADC, right? And as I mentioned, this was popular in the olden times. I mean, olden times meaning till up to 10-15 years back, simply because people were doing pipelining with flash ADCs, and in a flash ADC, if you reduce the number of comparators, it is good, right? Because in flash you need so many comparators. You reduce the number of comparators, it is a nice advantage. But in the recent past, all the pipelining is being done with SAR, right? Almost all flash has been replaced with SAR ADCs. So we now have only what is called pipeline SAR. We look at it shortly in detail. So almost all places flash ADCs have been replaced by SAR now. So in a SAR ADC, this is not so significant because in SAR you already have only one comparator. So it doesn't make any sense to have this. So this is not commonly used, but it is still good to know this. And again, this switching from flash to SAR is not something incidentally that happened. Okay, if you think about it, the timelines, as I mentioned, this idea of pipelining is pretty old. Okay, this first pipeline ADC came in 1970s or 80s. Similarly, SAR people have been knowing it for a long time. But as I mentioned, SAR was always done in a synchronous manner by feeding the high frequency clock. Only in the late 2000s, people discovered we can do this asynchronous SAR by having the flip-flops and the gates and stuff, which means you no longer need a high frequency clock. You can feed in a low frequency clock and make it. And once that got established in 2005-06, SAR got exported like anything. And the first time this SAR was pipelined was around in 2010 or 11. So that sort of, I would say that asynchronous SAR was sort of the starting point for this entire business. And that was all possible because some guy understood that clever digital circuitry and signal processing can be combined in analog circuits to solve huge problems, right? So let's stop here. But I mean, still this 1.5 bit stage is nice thing to know, because in some places people still use this.